Hello, and today I'll be showing you how to advect your particles using a vector volume. So, I'll remove my pop network, I'll also remove the blast here, and I'll walk you through the scene quickly. So I have a torus where I'm scattering some points inside of it and animating the jitter seed, like so. Then essentially this setup is created by the billowy configure billow smoke, and this is the result here. We do not need actually to export our densities. Well, disable it. We only need the velocity. By the way, you don't need to crank up the voxel size very low because velocities, generally speaking, could be with a higher voxel size and you won't actually notice the difference. So I'll create a pop network and I'll plug in the first input my points and in the second my velocity volume. So what I'll do here is I'll be sourcing all points. I'll disable the guide and life expectancy, let's set it to 2 seconds, and the life variance to 0.5. Like so, we can see now it's sourcing something, and I'll place advect by volumes. So, in here, I'll set the second geometry context, because that's where we're importing our velocity field. Here you're specifying the vector field you're trying to advect particles from, or based on. In this case, it's vel. Also, the velocity scale, you can change it. Then update force, you can play with different types. I'll keep it to update force, or you can play with different advection types. Of course, you can control the air resistance and so on. So I would like to talk about the advection method. In this case, it's at a single step. Single step is fine, but the disadvantage of a single step is that the result is less accurate, but it has the advantage of it being faster, so less computing. Trace is sometimes used also. It's a also very commonly used one. And this one is more precise than the single step, but it takes more computing. I generally speaking use trace. I feel like it's more precise and the computation isn't that long, but in some scenarios single step should be fine. The CFL condition. So the CFL condition is a parameter which controls, essentially, the higher the CFL condition is, the less iterations the advecting has to take, or the advection has to do, which means that there's less computing, which is going to result in a faster, quicker result. But the downside of increasing the CFL condition to larger values like 2 or 3 is that the result can have more errors, or is simply going to be less precise. But yeah, you get the benefit of quicker computing. When you're lowering the CFL condition, that would mean that there are more iterations per each advection, but the result will be much more precise. It's good to keep it somewhere in the middle, where you have enough precision, and also it's not very heavy for computing. Also, you can use vex expressions. So yeah, one last thing I'd like to add is a pop color. A pop color where I'll take the length of my velocity just to better visualize it. Fit range it from 0 to 5 to 0 to 1, and then take, let's say, Inferno, like so. I hope you learned something new. You can also Google the CFL condition on Google. It should give you some results. It's commonly used. Also, you can see CFL condition in Pyra solvers, inside flip solvers, in many different types of fluid simulations. It's a very common thing to see. So yeah, I hope you learned something new, and I'll see you again. Bye.